Let us do the common source amplifier simulation right now. Before you do the simulation for the common source amplifier, we should know about MOSFET. So for that sake, what I do is, I'll be taking a MOSFET cases where I'm trying to vary the gate voltage once and varying the drain voltage once, and observing the variation of the gate voltage on the x-axis and observing the variation of the drain voltage on the x-axis, and similarly I'm observing the drain current on the y-axis over here, so that I will be observing these characteristics. We call this one as a transfer characteristics and we call this one as a output characteristics. And now what I do is, I will be taking the transfer characteristics. I will be taking the transfer characteristics and I will be going with some kind of analysis on transfer characteristics, and I will be extracting the basic property of the transistor. The basic property of the transistor MOSFET over here is, where you see the characteristics once again. So the characteristics will be like this, and there will be a drain current which will be observed on the y-axis by varying the gate voltage VGS. And while we are varying the gate voltage up to some extent, we call this one is a VTH. So up to VTH, the drain current is 0, and from the VTH there will be current will be conducted like this. So we see this graph as a parabola, and we know the curve equation for the parabola is there is a y-axis is id, y is equal to mx square. That is what parabola curve equation, where x-axis is VGS and y-axis is id. But what happening is, the curve is not started at a 0, it is started at VTH, means the curve is shifted by x naught units. X naught units in the sense, so we will be getting the curve equation like this: x minus x naught whole square. So m into what is x-axis? VGS is my x-axis, and that particular curve is shifted by VTH units, so that VTH whole square, and y is nothing but y-axis is nothing but id. So I will be putting my id as it is. So over here m is nothing but a constant over here, that we can derive it. It's not that easy, so that I cannot do the derivation for the m. I'm keeping that m value as it is, of mu cox w by l times of VGS minus VTH whole square. So this is the curve equation for the ID. It means the transistor over here, when you give the gate voltage of VGS and having a threshold voltage of VTH and having the width of W and having the length of L and having the mobility of mu n and having the oxide capacitance of cox, then automatically based on all the parameters, he will be expecting the current of ID. He will be expecting the current of ID. So now what I do is, I will be calculating the ID is nothing but a salary he is expecting, right? Based on the salary, how that particular transistor expects the salary, and the biasing circuit, is it generating the same salary, so that the transistor will be operated in the region where it can do the controlling. So as we know, if you refer that case of BJT, is a current control current device, where the controlling operation is only done in the region. So if you see the transistor BJT case, this is BJT case, the characteristics will be like this, where in one region you call this one is a controlling region, we call this one as a active region, and this is what a saturation region, this is what cutoff region. Only this region where IC collector current, if it is conducted around beta times of IB, so he will given a IB current and beta times of that much. When the transistor is expecting beta times of IB, if the same current is pumping by the supply over here, the transistor automatically it was operated in the active region. Only in that region it is a current control current device. Current control current device. So that and all the analysis we have done with BJT, and we have to know the same thing in place of BJT. If you see, now we have a MOS transistor. Now we have a MOS transistor. Now coming to the operations over here, MOS transistor, here it is operated in the saturation region, and it is a linear region, it is a cutoff region as it is. Cutoff region as it is. Now when I am expecting the transistor BJT to have a control, current mechanism, it was there only in the active region, where in the case of MOSFET, the voltage controlling current device is not a current device, voltage controlling current device. So this controlling mechanism only that MOS transistor will be having when it is operated in the saturation region. So for that, what I have to do is I have to provide the drain current over here. So there will be a biasing circuit should be connected such that it should be generating the drain current. It should be greater than, so whatever the current he is expecting. This is what the current he is expecting. So he is expecting that current IT is equal to half mu COXW by L. How you have calculated. So he is expecting that my biasing circuit need to generate that much so that the transistor will be operated in the saturation region. So you will be having the mechanism of voltage controlling current device, right? So let us see how the particular voltage controlling current device mechanism that transistor is having is. So here I have the transistor circuit, biasing circuit. So let me take a screenshot of this one. So now coming to the transistor, let us calculate the drain current, how much he is expecting is. The drain current, how much he is expecting is. So actual thing is the gate voltage is not 2.3. So if you give the double click on that, we can see that actual voltage. It is around 2.26. Around 2.26. So now let me write that gate voltage of 2.26. Gate voltage is 2.26 and threshold voltage. So after like you give the double click on the transistor, once you do the connections, that threshold voltage of the transistor is so this is the value threshold voltage only. So threshold voltage of the transistor is 2 and beta value of the transistor is this one. So let me take the same thing as a reference. So let us take the same thing as a reference. So threshold voltage is 2 and beta value is this one. So let us calculate the current which is expected by the transistor is, as we know the formula of ID is this one. So let us update that mu. And in this tool what it is showing is he will not ask you the details of COX and W by L, and what he will do is this end term is represented as the beta. It is taken as a beta. Yes. So what we do is the beta value is mentioned around 97. So I will be taking the 97 milli as it is. And VGS minus VTH. VGS is nothing but the value of VGS is around 2.26. So 2.26 minus VTH is nothing but the threshold voltage which you mentioned there. It is the possibility that we can change the threshold voltage on the tool. So this is the tool. If you give the double click and the threshold voltage you wanted to maintain 1.5, let's suppose, you can change it to 1.5. Yes. And the value which I have with around 2, which is given as around 2. So after you give the threshold voltage of this much, beta of this much, and give the gate voltage of this much, and now calculate the threshold voltage over here is, sorry, current over here is 97 into 0.26 into 0.26 divided by 2. So he will be expecting the current of 3.2 milliamperes. So 3.2, he will be expecting 3.2 milliamperes. But what is happening is the biasing circuit is able to provide 3.3 milliamperes. She is providing 3.3 milliamperes. So now I can say the transistor is getting more than the expected current. So he is expecting 3.2, but he is getting 3.3. So for sure it will be having a mechanism of voltage control current device mechanism. So the transistor for sure it will be operated in the saturation region. So let us verify that. So if I keep my cursor on the transistor, it will be showing the region of operation. We can see that the region of operation over here, it is a saturation. What I do is, if the transistor is operated in the saturation region, he is expecting the current around 3.2 or 3.3. So if the supply is that much, now what I do is, I will be increasing the supply. Or I decrease the supply. So I decrease the supply, right? I decrease the supply. So what happening is, even that VDD value is changed, supply is changed. So I'm trying to change the supply voltage from 10 voltage to 14 voltage. The voltage potential difference is changed. And when the potential difference is changed across the resistor, automatically current is also should be changed, but the current flow through the particular branch is not changed, because the control of the current flow, it is there in the hands of gate. So voltage controlled current device, as it has the mechanism of controlling the current through the gate voltage. So I didn't change the gate voltage, so that the current across the branch also will not be changed. So 3.3 is constant irrespective of the voltage which you change it. So the basic property of the transistor is a voltage control current device. That's what verified. Now what I do is, the gate voltage over here, so now I will reduce it. So I will be keeping it as a 2.1. Let's suppose I increase, so it's not a 2.2, I increase to 2.6 for suppose. So 2.6, I'll increase to the 2.6. So now when I give the gate voltage is 2.6, now what he is trying to do is, he is expecting the current of 11.7 milliamperes, as we calculate it again over here. So the current which is expected of that much, because of increasing the voltage. So increasing the voltage over here, it is 2.6. Let me keep the 2.6 over here. So 2.6 over here, this is the new gate voltage. Once like a gate voltage, drain voltage is changed from the 10 voltage to the 14 voltage, even though the current over here it is not changed, it is around 3.3, because that current flow, the control is not there in the voltage change, it is there in the voltage change of the gate. So now I am trying to change the gate voltage from the 2.26, I am trying to change it to, yes, change it to 2.6. So when I change it to 2.6, so let me calculate that current once again. The new drain current, it will be of that 97 milli as it is, and VGS minus VTH. VGS is nothing but 2.6 minus 2 whole square. So if I do the calculation, so over here what happening, 0.26 is now changed to 0.6. 0.6 times of 0.6. If I do it, it will be doing the calculation of 17.46. So he is expecting the current of 17.46, but how much it is pumping? That only 11.7 itself pumping, so that the transistor is getting deviated from the saturation region to the linear region, right? So now the transistor is not having the control, it loses its control. So whatever that current he is expecting, that much current if it is able to pump by the supply, the transistor will be in the region of operation where it has a control. So now because of that one, I increased the voltage, he is expecting the more salary around like 17 rupees or something. So he is not able to give the 17 rupees, he is only giving like 11 rupees itself. So what should I do is, I have to bring the transistor again into the saturation. For that what I do is, so he is expecting the salary of around 17 rupees, I have to provide the 17 rupees by adjusting the biasing. So what I do is, I will be changing that resistance over here, it is 1k, now I will change it to the 0.5k. So once I reduce the resistance, automatically it will be pumping the current more, so that you can see the transistor now came into the saturation region. So now the transistor is in the saturation region. So previously transistor not in the saturation region, so that it was in 1k. When it has in 1k, Okay, the transistor was not in the saturation region, so that if I change that drain voltage, if I change the drain voltage 11.3, immediately it was changed. There is no controlling. The current which is flowing across this one is having no control. Now what I need is, I just want to bring into the control mode. For that, what I am trying to do is, I will be changing that 1 kilo ohm to 500 ohms. So now when the transistor is in the saturation region, again he got a control. So whatever the changes you are trying to do, so 11.7, now it is not changing. Even though like we are changing the VCC, the current over here, it is not changed, because the current is controlled by this fellow. So transistor has its control over here when the sufficient salary is given. So now I can give the conclusion whether the transistor is need to do the control operation or not. It depends upon how much salary is expecting of mu COX W by L into VGS minus VTH whole square. That much current if you provide, so that much salary if you provide, so the controlling mechanism will be there and transistor will do the control. Yes. So now using the same basic property of the transistor as a voltage control current device, that same transistor can be used over there in the amplifier. Where in the amplifier application, alright, I have done the simulation for the amplifier. That I have given a biasing circuit over here, and I am giving like some input signal here. I am just observing that output is like having a faithful signal or not. And I know that there is an output with a faithful signal when the transistor is operated in the saturation region. Otherwise, will not have a faithful signal. And one more thing that what I know is, right, I'll just give double click on the transistor, and I will go with the edit model, and I can see the parameters of the transistor. So I'll keep this one and I'll take a screenshot. So now same analysis, right? I'm trying to do it on the multisim. This is where I have done in Falstead. Now I'm trying to do it in the multisim. Yes, and in the multisim, what it is showing is wherever you see the transistor when is connected, that basic property will be the same. So let us verify the basic property which we have verified in the Falstead or on the multisim also. So what we have to verify is, and we should know how to know the current which is flowing across the transistor. So this is where transistor is expecting the ID current. So let me calculate the ID current over here. ID is nothing but, as we know, that mu COX W by L times of VGS minus VTH whole square. The formula will be same and the operation is same, controlling mechanism is same, but the parameters which are there in the tool, right, in what way it is mentioned is different. So in the tool, what is mentioned is KP value is mentioned. So the KP value in the tool is this one, mu COX value. This value will be given in the tool. So previously this total value will be given in the tool and only this value is given in the tool. And the flexibility with the multisim is, we can change the W value and L value individually, so that when width of the transistor is changed, we can see that what will be the change of the current also. The extra feature is given. So now, right, what I do is, I will be calculating the current again over here. Mu value is mu value and COX value combinedly is given as a KP. So this value called as a KP is given around 20.7 micro into W value also given and L value also given. W value is around 9.7 milli and L value is 2 micro into VGS minus VTH. So here we can see, I can zoom it. So if it is not visible over here, I can go with the tool also. So here I can zoom it. So when that gate voltage over here it is, there is a gate voltage of 2.26. VGS is nothing but 2.26, and already we know threshold voltage also mentioned over here is around 2 volts. Yes, So because I'm taking these values based on the transistor which type I'm trying to use. So the transistor 2N7000 which I already used in the lab. So that's why like I'm taking the same transistor. So 2N7000 transistor will be having the threshold voltage of 2 volts, and the VGS which we have provided is around 2.26. So that's why 2.26 that is what VGS minus VTH is around 2 volts. I will be substituting over there, and now the value over here it is nothing but so 20.7 micro. You keep micro afterwards into 9.7 9.7 into, so the difference is 0.26. So 0.26 into square, in the sense I will be keeping the value 2 times, 0.26 into 0.26, and this value got it. Now divided by, you have 2 over here and you have 2 over here, divided by 4 I have to do it. This value divided by 4 I will be doing. So the value is around 3.3. We got it. So now coming to the units, this micro had cancelled, only you have milli. So now this much milliamperes he will be expecting. So the ID over here is expecting is around 3.3 milliamperes. So now let us verify that the transistor is expecting the current of 3.3 milli. So now he is able to pump around 3.4. So there is a resistance which you connected which is allowing the current around 3.4 milliamperes. So we don't have any problem that the transistor is expecting, he is expecting the salary around 3.4 rupees. So expecting the salary around 3.3 rupees, he is able to give the salary around 3.4 rupees now. So we are comfortable that more than he expected the salary was provided by the supply. So now the mechanism of controlling and transistor is operated in the saturation region, so we don't have any problem. The input signal can be amplified so that we will be getting a faithful signal. So now let us verify over here and let us run. So first let us verify that input, yes, this is what input, 2 units into 10 milli, so around 20 millivolts, that is what your input signal. Input is 20 millivolts because we keep like a 10 millivolts as a peak, so the 20 millivolts is given as input. And if you see the output, you make it input 0, so that we will see that output over here. So this is what we have output. So 200 milli is the one division, and you got it around 2.6 times. So 2.6 times, so 2.6 times of 200 millivolts is each division, so that output you finally got it around 520 millivolts without disturbance or without any distortion. You got this much. Yes. So now if you see this one, so this is what a transistor circuit, this is what your transistor circuit, you connected a load of this one, and we know that gain for the transistor circuit is, and we have done the calculation for the common source amplifier, and the voltage gain of the common source amplifier is minus gm times of rd. Rd is nothing but the resistance which are connecting it over here. So this one and this one, this both comes under that rd, overall resistance. So this one and this one is comes under the rd, and you keep the gm times of rd, right? So this is considered as a gain. Minus indicates like 180 degrees phase shift. We got like minus 180 degrees phase shift also here. So we can see it 180 degrees phase shift. Yes, we got like 180 degrees phase shift over here. So as per that gain formula that we got it, minus gm times of rd. So we got the input as well as output with 180 degrees phase shift. So now if you observe that the current of around 3.3 milliamperes need to be expected by the transistor, is expecting by the transistor. Because of this resistance rd, you keep the resistance of rd around 2 parallel with the 2, it is around like 1 kilo ohm over there. So for that resistance, what happening, the transistor was provided with a sufficient current of around 3.4. So he is expecting 3.3 rupees, he is able to give 3.4 rupees. So sufficient salary was given to the transistor, so that the transistor for sure it is operated in the saturation region. so that we are getting a faithful signal, and we have calculated the gain of theoretical calculation and practical calculated gain is around 500 sorry 520 520 by 20. It is around 26 times gain you got it. In the first case you got it gain around 26 gain. But what I need is I need more gain. So the option is to get a maximum gain across the common source amplifier. To increase the gain, I have an option that I can increase the RT. The pull-up resistance over here I can increase. So on that intention, what I'm trying to do is, in the second case and third case, I'm trying to increase the load devices values. So here I'm keeping, instead of 2 kilo ohm parallel with the 2 kilo ohm, I'm keeping 3 parallel with the 3. In the third case, I'm keeping 4 parallel with the 4. And in fourth case, I'm trying to go with the 5 parallel with the 5. So like that, if I increase the load resistance, for sure the gain will be increased, as that gain equation is saying that as you increase that RT, for common source amplifier, the gain is like GM times of RT. As you increase the RT, the gain will be increased for sure. So now I'm trying to do the same thing when I keep like a 3 parallel with the 3. So we are expecting 3.4 rupees for sure here. He's expecting 3.4 rupees. Even though we keep like a resistance also, like instead of 2 kilo ohms, I'm keeping 3. So resistance increases, in the sense there is a possibility the current will be limited, but is not limited over here. So this person also, this HR also is able to give the same salary what he is expecting. So 3.4 rupees he is able to give. So now we can say, right, so the output is over here, input will be the same, I will not calculate. Output is 4 divisions over here into 200 milli, 4 divisions into 200 milli, 800 millivolts. So now what happening is, in the first case, when I keep RT is equal to 2 parallel with the 2, I got the gain of this much. And when I keep like RT is equal to 3 parallel with the 3, again how much I got it, 800 by 20, I got it the gain around 40. So I could increase the gain from the 26 to the 40 by increasing the RT. So now I will be having more, I need more gain. For that I'm trying to go with the next case, I'm keeping 4 parallel with the 4. So and I will be verifying the gain, is it getting increased or not. But unfortunately what happening is, so when I keep the resistance over here is maximum, resistance over here it is big maximum, so he is trying to limit the more current, so he is not giving the salary what he is expecting. So 2.26 volts, we calculated the current which is needed for him to operate in the saturation region around 3.4 millivolts is required. So he need around 3.4 rupees, but this biasing circuit only giving 2.9 milli. So he expect like 3.4 rupees, he is giving only around 3 rupees only. So the transistor will be going away from the saturation region. So we can see that the waveforms over here. So waveform over here. Yes. So this is what output waveform. So we expected that there should be spread out up to 8 units, and after you keep the resistance more, it should be spread more than that 8 units, but it's not going to be happening. So it is getting limited. So here onwards we can't do that increasing the resistance, and further that we cannot increase the gain. So this is the max value, up to 3 and 3.3 we can increase the gain. So how we can increase the gain by increasing the RT, and what is the limitation that we have while increasing the gain, and we cannot keep the resistance whatever that we want, and with keeping the maximum resistance, how the transistor is getting deviated from the region of operation, and how uh, the particular amplifier is getting failed in doing the task. So that's what we observed over here by observing the basic property of the transistor.